Hello students, we'll try to solve a few questions from chapter 5 of SC Verma. The chapter is Newton's Laws of Motion, chapter 5 SC Verma. So we'll see question number 10, question number 11 and question number 12 today. So in question number 10 we have two springs of spring constants K1 and K2, a mass m is attached in between them, and the question is if a distance x, the mass is moved a distance x, what will be the initial acceleration? So if we move the mass x in this direction, the spring K1 will expand for a distance x and the spring K2 will be compressed by x. So we know that the force exerted by a spring is equals to minus kx. That means in the opposite direction of the elongation or compression. So in this case we will be having two forces. Since it is expanded, it will pull towards itself. Since this spring is compressed, it will push away from itself. So in both the cases force will be in the same direction. So the total force acting on the mass will be K1x plus K2x. So by applying Newton's second law, that force equals to mass into acceleration, so we will get acceleration equals to K1 plus K2x by m. So this will be the initial acceleration as the mass m is released after a distance x is moved by it. So this will be the answer. The acceleration of course will be changing in the path because this force will keep on changing. So that calculation of that acceleration will be a function of x actually, and that will be different way to solve the question, including we have to use calculus for that. So in this question it was asked only the initial acceleration, so we directly equated force equals to mass into acceleration and we got the acceleration. So we'll see the next question, question number 11. There is a small block B kept on a large block A. The block A is having a length of 20 centimeters and the weight of block A is 5 kgs. So the block B is here initially and 10 Newton of constant force is applied on block A. All the surfaces are assumed frictionless. We have to find the time B takes to fall down from here. So when we see the body A, we see that there is a 10 Newton force horizontally applied on it. We are not concerned here with the vertical forces because the vertical forces are going to be cancelled out because there is no motion in the vertical direction. So we see that the block A is being applied a 10 Newton force in the horizontal direction. So when we use second law, Newton's second law, so force is equals to mass into acceleration. So 10 Newton equals to 5 is the mass of the block into acceleration. So we get the acceleration 2 meters per second square in this direction. So this is the acceleration of block A. Now we have to find what is the time elapsed by block B to fall on A. So block B will be maintaining its inertia because there is no friction force here. So block B will try to be stable on that single position itself and block A will move forward. So in that case, when we see the block B with respect to block A, we find that the block B is moving in this direction. If a man is standing on block A and he is seeing the block B, he will find that the block B is coming towards him. So this is how we use thus Newton's second law when we apply Newton's second law through a frame of reference which is not inertial. So in this case, if we take A as the frame of reference, so this frame A is not inertial because it is having an acceleration. So in this case, as you all know, we have to apply a pseudo force in the opposite direction of the acceleration of the frame. So the frame here is block A, so we are standing on block A and watching the block B moving on the surface of block A. So we have to apply a pseudo force in the opposite direction, which will be equals to the mass of the block and the acceleration of the frame. So it is mass of the block B and the acceleration of the non-inertial frame. So mb into the acceleration of A will be the pseudo force applied on block B. When we want to use Newton's second law on B, when we are seeing with the frame of reference A which is not inertial. So in this case, we'll again apply the Newton's second law. So that will be mass into acceleration. So this is the pseudo force. Force equals to mass into acceleration. So we have to be very sure that this is pseudo force. There was no actual force acting on mass B, the block B, and we have applied block B because we want to use Newton's second law on block B using by seeing through the block A, by using block A as the frame of reference. That's why we have applied a pseudo force here. So we get the acceleration of B will be equals to acceleration of A. Of course, this will be in the opposite direction because we have seen that the pseudo force is acting on in this direction. The pseudo force is always applied in the direction opposite to the direction of the frame acceleration of frame of reference. So we find that the acceleration of B with respect to A. We have to be clear here that this acceleration of B is with respect to A, that is equals to 2 meter per second square in this direction. So this is in this direction. Now since it is in this direction and we are actually seeing it with respect to A, then we can see that the block B is actually having initial velocity 0 and it is moving with an acceleration of 2 meters per second square, and it has to cover a distance of 20 seconds, and we have to find the time elapsed in this process. So we can simply use the formula s equals to ut plus half at square, where s will be 20 by 100 since it is in centimeters. Initial velocity is 0 plus half into acceleration is 2 into t square. So we get t equals to under root of 1 by 5 seconds, that is approximately equals to 0.45 seconds. So the answer in this case will be 0.45 seconds. Fine. So this will be the answer. So we'll see the next question, question number 12. The question number 12 says that a man has fallen into a ditch and the width of the ditch is d, and two of his friends are pulling this man with a rope, and that rope is fixed through a pulley, and we have to assume that both the friends are applying equal forces, and we have to find the force applied by the friend when the man is at a height h, I mean at a depth h from the pulley. So in this case, and we have another question also, we have to show that the force exerted by each friend on the road increases as the man moves up. So this, if each person is exerting some force on the road because they are getting some if they are not exerting force on the road, they cannot lift the man. There will be friction force actually in actual case we'll learn in the next chapter that what the force this man is actually applying on the ground is the friction force. So this man is applying friction force, is pulling the ground backwards, and this man is pushing the block the ground forward, and the ground is pushing the man in this direction so that this person can actually pull the rope. So the man has to actually apply some force on the ground so that he can pull the man. So in that case we have to show that as the man is getting lifted upwards, the force which they have to apply actually increases. So we'll try to prove that. First we'll find what is the force of the man when it is at a depth, force applied by them when the man is at a depth h. So we draw a line diagram here. So we see that there is a tension acting along the string. The mass mg is acting downwards. This is again a tension. Let's say this is angle theta. This is half of the width of the ditch. So this is d by 2. So we see that in the upward direction there is two forces, t cos theta and t cos theta. So 2t cos theta is equals to mg. So we are assuming here something, that the acceleration is actually 0 in this case, because we assume that the friends are actually pulling the man up with very small speed or very slowly. That means it's or very slowly and constant speed, and they are not actually giving more force to bring him up with an acceleration, bringing up with an acceleration. So they don't want any acceleration to be there. So we are actually seeing here a case where these people are actually pulling him up very slowly. So we assume that there is no acceleration and they are pulling the man with near to 0 velocity and very slowly, and that velocity is constant actually. We don't consider acceleration here. So in that case the forces upwards and downwards will be equal. So 2t cos theta will be equals to mg. So cos theta here will be base by hypotenuse, so it will be h by h square plus d square by 4 under root, that is equals to mg. So we get T here. So this is the tension applied by the string, tension in the string for the man to be pulled up when the man is at a depth h. Now, so we have got tension as a function of h here. So now we have to prove something else. We have to prove that both the men, this will be answer for the other part of the question. We have to also prove one more question here, that both the friends exert the whatever the force they are exerting, it actually increases as the man is going up. So what we'll do is we'll differentiate tension here. So actually, whatever the man is putting the force on the ground is actually transmitted as tension in the string. So this we have to actually concentrate on tension here. So since we have got the tension here from this equation, so we will actually differentiate tension with respect to h. We'll see why we are doing this. So we differentiate it. This is a function v in the form of u by v. So we have v square, and the differentiation goes something like this: v into du by dx minus u into dv by dx. So this way, when we differentiate it, and what we finally get is, so the differentiation of t with respect to h, we are getting, we solved and we got this one. So you can see this how the differentiation has been done. I'll not go into the details. This is simple mathematics. So the differentiation of t with respect to h comes to be minus mg d square by 4h square under root of 4h square plus d square under root. So you see here that the rate dt by dh is negative actually. So what does this mean? When we say differentiation or dt by dh, this means that it is the rate of change of tension T with respect to h. So rate of change of tension with respect to height is negative in this case. What does that mean? When one of the quantity decreases, the other increases. When the other increases, the other will decrease. This means that as height increases, tension decreases, and as height decreases, tension increases. Right? This is okay. So since rate of change of T with respect to h is negative, we have got this, that when the height is decreasing, when the depth is decreasing, the height here is depth actually. When we say the depth is decreasing, that means the man is going up. So when the man is going up, or when we say that the depth is decreasing, then the tension is increasing in this case, because the rate of change is negative. So now as the man goes up, the height decreases. The tension, that is the force applied by the friend, increases. Now the friend applies more force on a string, but this force is ultimately gained from the friction exerted by the ground. Thus the force applied by the friend on the ground is more. Now what we have seen here, that whatever the person is applying the force on the tension, he is getting that force from the ground actually. So as much force is applying on the tension, he has to apply some force on the ground also. So the force actually is friction force here, because you can see it in other way, that whatever tension is applying, when we consider this man as an object, so a force T is here and a friction force is here. We'll learn friction in the next chapter. A force friction is in this object opposite direction. These two are equal actually, because this man is not moving, so these two has to be equal. So how much ever the force he is applying, more force he is applying on the string, the more he will actually be applying on the ground also, so that he doesn't move. So in this case, we know that the rate of change of tension with respect to height is negative. So we conclude that as the height is decreasing, the force applied by the man on the ground, that means ultimately the tension is actually increasing. So this way we can prove it. Thank you friends. That's it for today. Thank you.